Hey everybody, Miss P here. Taking a look at a question that we kind of started to look at last week. And the question was, what does the area under the velocity versus time graph represent? And you were asked this question it was the beginning look of the quantitative graphing. This was question 4C. And when asked this question, many people gave me the answer that it means that the object is going towards the reference point. But that's not quite right. Now I can see why we would think that, because if you're thinking, oh, something is underneath, then it's probably negative, and a negative means that you're going towards. But the key word was the area. So what you would actually want to do is look at what the area of the rectangle means. And what it actually means is that the area under the velocity versus time graph equals displacement. So why is that? So if you actually take the area of the rectangle, meaning length times width, what do the units tell us? Now, when I say area under the curve, this horizontal line is your curve. And then the area underneath it is to the x-axis, so making this rectangle. You wouldn't go any further because that would be like infinity, so you have that definitive point of the x-axis and your curve. So when you take the area, so your length times width, and look at them in terms of the units, you get meters divided by seconds, multiplied by seconds. So you have a seconds in the numerator and a seconds in the denominator, which cancel to give you meters. Well, meters is a length measurement, and if we're dealing with the length measurement and velocity, that brings us to displacement. So your delta x, this is telling you how far you're going between your xi and your xf. So what would the displacement be for the above question? Well, all we need to do is take the area, where we take 10 meters per second multiplied by 5 seconds, and you find out that you travel 50 meters in 5 seconds. And we could actually plot this point. So assuming that your object started at the reference point, so 0, 0, we could then go to 5 seconds, go up to 50, and then we'd have our line. So that's what we had to do in the example problem that I gave you in the learning plan. So the first thing I said is I wanted you to create the position versus time graph, and I actually told you what your starting point was. I said it was 0, 0. And what you would have to do before you would put in any of these numbers on the position side, time we can put because that's going to be the same, is you have to take the area first. Much like when we were creating the velocity from the position, we had to take the slope first to know the numbers. Well, in order to go backwards and make that position, we again have to know the numbers before we can do anything. So taking the area of section 1 is the 1 meter per second times 5 seconds gives you 5 meters. Nothing happens in section 2, you're just not moving. And then section 3 is that -2 multiplied by 2.5 gives you the -5 meters. So imagine if this was your walk it out lab, it's pretty much like you started at your reference point, walked away slowly, stopped there for 5 seconds, and then quickly went back towards the reference point. Knowing these values, I can then plot them on the position versus time graph. So if I start at 0, 0, I know that by 5 seconds I need to get to 5 meters, then I don't move, and then I head back towards the reference point. That's what that -5 is indicating, and I do so quicker than section 1, so we should see that steeper slope. Then making the model, we know that we already have that basic function for velocity or constant velocity, which is xf is equal to vt plus xi. And we only put in numbers that are constant when we go ahead and customize this, because we want this equation to be able to solve for anything that we could potentially look for. But we know that velocity doesn't change for the section, and the initial position also doesn't change, so we can put those numbers in. So the velocity for section 1 was just 1 meter per second. The initial position was 0, so we don't have to write it. For number 2, you're not moving, so velocity is 0, and 0 multiplied by anything is, well, 0, leaving you with just your initial position that you started that section 2 at of 5 meters. And then your last mathematical model, this is the one that changes just a little bit. We go ahead and we put in that velocity of -2 multiplied by t, and then section 3 does have that initial position of So always do remember that you're looking at initial positions, not y-intercept anymore. Like that's way gone now. We've used it, we've moved on, and now we're saying what is the initial position of this section. Then the last question, or at question 3, says what is the exact position of the object at 11.26 seconds? Well, 11.26 seconds occurs in section 3. So how long are you actually going -2 meters per second before you hit that given time? Well, you're only going 1.26 seconds. Plugging that in, you end up getting a value that makes sense, because if you go to the 11.26, you're somewhere right around here, which is indeed right around 2.5. So we check our number with our graph and we see that it makes sense. Had you just straight up plugged in 11.26, you'd get an answer that didn't make any sense at all, because you would be assuming that you went -2 meters per second for that entire length of time, and you didn't. You only went -2 meters per second for 1.26 seconds. All right, and then all you would do for the last question, so determine the average speed and the average velocity. Well, average velocity should be a very quick answer. You start and end at the same point. So if you start and end at the same point, xf minus xi gives you 0. And that's a very quick answer that we can give. Now, determine the average velocity. Well, if we're thinking about an odometer reading, we go up 5 meters, nothing happens, and then we go down 5 meters. So in total, the object traveled 10 meters over 12.5 seconds. So all you would need to do is 10 divided by 12.5. All right, see you later.